Welcome back. So this is the third video, or what? Or is it officially the second video we have in this series? So in this video we are going to be looking at, we are still within concept of numerical analysis, but like I told us in the last video, we are looking at types of error this time around. So if this is the first video you're going through on this series, I'm going to put in the link in the description below, the link to the previous videos. Go ahead and watch them before you come for this video. Okay, so we are looking at types of errors. So in the last video we discussed the true error. What we actually discussed then is called the true error. That means true error is basically when you have the actual value and then you have the numerical value. So the actual value minus the numerical value gives you the true error. Now, as you can guess, this is most times okay. Let me just give you an example first. So we have an example to be the actual value being 10 and the numerical value being 10.6. So if the actual value is 10 and the numerical value is 10.6, they are going to get a result with minus 0.6. That's what you're going to get. Okay, minus 0.6. But as you can guess by now, this value you have here is negative, and most times we are not interested in if the value is going to be negative or positive. We just want to know what's the magnitude of the value we are getting. So for you to tell the magnitude of a value, that comes the second method. Okay, that's where we have it now with the second type of error. So the second type of error you have, for you to get the magnitude, you look at the absolute error. So the absolute error is basically when you have the true error, which is this, and then you take the absolute value of this true error. And absolute value in this sense here simply means you're ignoring the sign. We can picture it that way in the layman terms. Okay, it means far more than that, but let's picture that you're ignoring the sign. So this is what we have for the absolute error. It's simply the absolute value of the actual value minus the numerical value, which is always going to be positive. So absolute value is defined to be a non-negative value. So it's either going to be positive or it's going to be 0. A good example is we having still that same value. We have 10 being the actual value and 10.6 being the numerical value. Our error here is 0 minus 0.6, but when it comes to the the absolute error, it takes away the negative sign, as you can see here. So if we take away the negative sign, what we are going to have there is going to be just 0.6 because the negative sign is being cancelled out. Okay, so this is what you have for the absolute error. That's the second type of error we have. And next we have relative error. So what I mean by relative error is simply you have this actual error, but most times the absolute error may not give you a true representation. It may be falsy. It may give you a value that you think the magnitude, you can't really measure the actual magnitude. Let's say you have the actual value to be very small. Assume the actual value is something like 0.0001, and then you now got the numerical value, the numerical value to be 0. Let's say 0.0011. So here your difference, which is the absolute error, is going to be very small. It's going to give you something like the absolute error will give you 0.0001. Right? I think that should be it. Now when you see a value like this, you may think that, hey, the error that is made here is not actually much because the value I have here is quite small. But that may not be the case. It may be that this error is quite large and you can't tell because you're just using the absolute error. So for you to compensate for this so that you know how large this error is, we now have to come up with the relative error. So that's the next one we have, is called relative error. So relative error is simply the actual error, the absolute error, divided by the actual value. Okay, so like in that case we had this relative error is going to give you about 0.0009, that's 0009, right, 0001, they were dividing by 0.001. I think this is what you have, and when you compute this, I think this will give you about 0.1 error, which is about 10% error if I'm not mistaken. Okay, you can go ahead and verify that. Okay, but that's what the relative error is. The actual error divide the absolute error divided by the actual error. So in terms of more precise mathematical notation, you have something like this. And let's see some other example this time around. We have this to be the relative error, so you can see the value is 0.6. But now we want to express relative error in terms of percentage, because relative error generally lies between 0 and 1. It is unlikely for you to get 0, it's also unlikely for you to get 1. When you have a relative error of 0, it means there was actually no error. When you have a relative error, of 0, yeah, it means there is no error. When you have a relative error of 1, it means you have, in fact, the numerical method is not giving any solution because you have 0 as a numerical solution. So it really doesn't also drive the point home. So what we want to do is, it does actually, but those cases are unlikely. Okay, they're unlikely. You can get, those are two extreme cases that are actually impossible for you to get. You getting a 0 as a relative error, or you getting a 1 as a relative error. Okay, so let's say we want to express it in terms of percentage. If you are expressing something that lies between 0 and 1 in terms of percentage, then it's going to be between 0 and 100%. Okay, so basically what you need to do is to pick whatever you have here and multiply it by 100. So our relative error, this is going to be the percentage relative error, is going to be the absolute error divided by the actual error times 100%. Okay, so if we take our example, x being equal to 12 and the x cap being equal to 11.3, you can see here that if you look for the relative error, the actual error is going to give you 0.7. Okay, if it's 0.7, the relative error is 0.7 over 3 over 12. So this is not meant to be here. So 0.7 over 12 times 100% is going to give you approximately 5.83%. Okay, now you can see we'll carry out an approximation here. This is also going to lead us to some kind of error. So this is what's going to lead to the next type of the next topic we are going to be treating, and that's going to be sources of errors. Like now we've rounded off a value, we've gotten one source of error, which you can guess the name by now. But if you can guess the name, when we see in that section of sources of error, I'm going to tell you the name of this, and then we'll see other things we can look at. However, in the next video we are not going to be looking at the sources of error. What we are going to be looking at in the next video is how to code what we have here. We are going to use functions to in Python to generate a formula or a function that is going to help us compute the true error when we give it some values, to compute the absolute error, to compute the relative error, to also compute the percentage relative error. That's what we're going to be looking at in the next video. Okay, so as usual, if my videos are helping in any way, they are being productive to you, go ahead and like, subscribe. Okay, and I'll see you guys in the next video. Bye bye.